Hi, everybody. We're going to get started with session 11. 5 great talks. We have 3 students, and this is, I think, the last session, so make sure that you get their evaluations in. So we're focusing on where the ice and ocean meet. Awesome topic. And we're starting with Michael Field.
Hi, everyone. My name is Michael Field. I'm a third-year PhD student at UF, where I work with Mickey and Nia. And today I'm going to be talking about work I've been doing on improving estimates of sub-ice shelf bathymetry in the Thwaites region, and incorporating MCMC and geostatistics to improve the uncertainty quantification. So the reason that we want to study the bathymetry beneath ice shelves is because warm circumpolar deep water moves up the continental shelf and interacts with the base of the ice shelf, causing melt and leading to ice shelf thinning and increased mass loss. And as you can imagine, the general bathymetry controls how that circumpolar deep water circulates and mixes and its residency time near the grounding zone. So that's why we want to study the bathymetry. However, previous bathymetry estimates have not robustly quantified uncertainty because they haven't produced a spatial uncertainty. So we just have kind of single kind of error budgets. They've produced single inversion results. And they've used deterministic interpolations of the Bouguer disturbance. And I'll talk about more about what that means in a second. But basically that means that we have only one version of what the the subglacial geology might look like. And on the left, you can see the bathymetry from Jordan et al. 2020. And of course, Kirsty was the first in 2011. So really, inverting for bathymetry using airborne gravity is poorly constrained and fundamentally non-unique. And we need to quantify uncertainty in a way that produces multiple solutions so that we can take ensembles of bathymetry models and put them into ocean and ice sheet models in order to propagate the uncertainty in the bathymetry into basal melt, for example. Now, the sources of uncertainty are the measurement uncertainty, the background density, and unknown geology. And the 2 in red, those last 2 ones, those ones are inherent to the inversion. And I'm specifically going to be focusing on the unknown geology, because this has been the gap, in my opinion, and what's been missing in previous inversions. But before I jump into that, I just want to orient us. So we're here in the Amundsen Sea. This is Dotson Ice Shelf. That's Crosson Ice Shelf, and the Thwaites Eastern Ice Shelf up there. We're using ITGC and OIB gravity data, and this figure shows the extent of the radar and sonar coverage, and you can see this clear kind of massive hole in the center. And that's going to be where our inversion domain is. And it's also just to remember the extent of these constraints, because that's what allows us to constrain the inversion. But also of note, we're incorporating new seismic soundings from Muto et al. 2024, just very recently pushed to the data center. So back to the question of unknown geology, how can we broach this uncertainty? Well, first of all, where does geology live in terms of gravity data? So the Bouguer disturbance contains the gravity due to crustal density variations as well as crustal thickness. And how you find it is first you forward model the gravity due to the terrain, or this is just the gravity due to what you think the geometry looks like. And then if you remove that from the observed gravity disturbance or the free air anomaly, you get the Bouguer disturbance. But now the thing to keep in mind is that we don't have an accurate representation of the geometry. So we actually don't know the terrain effect or the Bouguer disturbance. And the funny thing about bathymetry inversions is that we need to invent this and subtract it from the free air anomaly to get a target terrain effect, and that's the actual target of our inversion. And I feel like in the literature we haven't, that's been obfuscated a little bit. So I just want to make that clear. And the real critical point here is that however you choose to interpolate this, to make this, that's what's dominating the inversion. So if you do a spline interpolation, you do minimum curvature, you could Krieg it, you could do radial basis functions, whatever. But all those methods are going to give you one map of what that looks like. You get one target terrain effect, and you get one inversion result. And in my opinion, that's inadequate. So the approach that we're taking instead is we're going to use geostatistics in order to simulate different versions of what the subglacial geology could look like based on the data that we know from the Bouguer disturbance where the bed is well constrained. So if you remember the map of the extent of the constraints I was showing you, we have a pretty good idea of the bed, outside of here where I've removed the data. So we can make a variogram of what that looks like. This is just a measure of the spatial dissimilarity. So as we increase in space, things get more dissimilar. We can fit covariance models to that. And then we can use sequential Gaussian simulation to create different versions of reality, of what the subglacial geology might look like, kind of indirectly through the Bouguer disturbance. So these two panels on the left show two different sequential Gaussian simulations. Then we have the mean and the standard deviation. And this is what is really going to drive most of the uncertainty in the inversion. We then solve our inversions using a Markov chain Monte Carlo method, where we use random bull updates. So the inversion process looks like this. Each iteration, we take the current bed model, we do a random block update, we generate the rectangular prisms, which is our model of the Earth. We forward calculate the gravity, then we calculate the metropolis acceptance probability, and then we accept or reject this update. And this is all it is. It's quite simple. There's no gradients, and it just keeps going until the error with the data is lowered enough. So using this method, we're able to really efficiently solve these inverse problems, which is really important because we're trying to do this many times with many different simulations of the Bouguer anomaly. So this first panel, this is what the reduction in the RMSE looks like. And this actually, each inversion only takes between 3 and 5 minutes, so it's quite efficient. And this is what the acceptance rate looks like. See if I can play this animation. This is what the inversion process looks like. I'll just play it again. So hopefully you can see how the inversion proceeds. I can't advance. Okay, sorry about that. So if we do that 100 times with 100 different SGS realizations, then we're able to quantify the uncertainty due to unknown geology that we've used geostatistics to simulate. So on the left, we have the mean of the ensemble. We have the standard deviation, which you can see goes up to about 200 meters in some places. And the right shows the difference between the mean and bed machine. And you'll see that there's differences of over 400 meters in some places. Okay, and then instead if we use a constant Bouguer disturbance, that's the mean of those SGS realizations, we see a very different character. So the uncertainty is much lower, and it has a kind of different spatial characteristic. And this ensemble is representing uncertainty due to just the measurement uncertainty. However, we see a very similar difference with bed machine. Okay, just really quick, I want to show you what this looks like in profile, so you can really appreciate some of the variability that we see in these models. And just skip through this. But the thing that I really want to leave you with is that, so the really important thing here is that now we have a bunch of different bathymetry models, which is sampling the uncertainty of the problem. And the whole point of this is that we can use these different bathymetry models in ice and ocean models to propagate the uncertainty in the bathymetry into basal melt and other processes. So, thank you.
Thank you, Michael. Michael's a student, so make sure you get your evaluations in. Next, we have a talk from Peter Neff, but he unfortunately couldn't make it, so he sent in a video. And it is 13 minutes long. So, buckle in.
Hey everybody, I'm Dr. Peter Neff. I'm an assistant professor at the University of Minnesota, and I'm sorry not to be there with you, but thanks for letting me share via video. I'm excited to talk about the fieldwork we conducted in the 23-24 season, collecting 2 new 150-meter deep ice cores and ground geophysical surveys at Gainesville Peninsula in the Amundsen Sea of West Antarctica, just about 130 kilometers north of Pine Island Glacier. This work was done with support by the U.S. National Science Foundation and in partnership with the Korea Polar Research Institute, who provided, of course, the RV Aeron and the lion's share of the field support. So I'm very grateful to them for the collaboration and to NSF for allowing us to partner up with them. I started talking about this project back when I was a PhD student. I just want to acknowledge sort of how we got to have this field opportunity and the length of time that it can take pursuing your passion projects, particularly in Antarctic science and these days when field logistics are a little bit tight. It's I think helpful to have that motivating big idea that you think you might not be able to do, but you can chip away at trying to find opportunities for and to get on paper and publish. So I started in 2014, almost 10 years to the month before we did the field work, talking about this at a U.S. Ice Core planning workshop. It then, in various WAIS Workshop talks sort of sustained through those years to 2020 when Amelia Chevenel invited me when she was a guest editor for this issue of the journal Oceanography to sort of get a 2-pager of this on paper and potentially get it in front of the community that might be interested from the marine perspective. And indeed, that led to my colleague Young Chul reaching out about 2 years later, seeing where we were at with the idea, and then eventually inviting us aboard the RV Aeron to give ice coring from the ship a try, which is something that the Korean groups had never done from the ship before. And then fast forward to January 2024, and our 2 teams, the US and Korean drilling teams, just a kilometer from each other on Gainesville Peninsula, collected these 2 150-meter deep ice cores. So it can seem like some of these things will never happen. I could certainly never expected for this to come together in the last year, but it has. So stay motivated about your passion projects for sure. I'll briefly go over, sort of Ice Core 101 motivation and why I try to show up as an Ice Core scientist at the WAIS Workshop. I think these records of climate we get from Ice Cores can allow us to explore processes, trends, and extremes at places and in times where we don't otherwise have observations. It gives us really important extended perspective on climate, environmental, glacier, and ice sheet sensitivity in a warming world to try to better constrain that key question of what's the future of the Antarctic ice sheet and how much sea level is coming towards all of us, how fast. It's pretty difficult to detect, the emergence of climate trends in Antarctica, given the length of the short records that we have and the extreme variability down there. So this is an interesting paper from middle last year, on just how hard it is, even having a 1,000-year-long stack of ice core water isotope, Delta 18O records there, and then modeled temperatures. And what they found is that the models really underestimate the impact of polar amplification on both natural variability and the magnitude of anthropogenic warming, which is really important to understand predicting Antarctic warming into the future. And so there's a huge offset there potentially between the contribution of sea level rise from the Arctic Peninsula and West Antarctica in particular, that's going to really care whether or not you are underestimating the warming in those places by a factor of 2. So we really need to get this stuff right and need a lot of observations to do that. I always like to highlight as well here in the red circle that we start to lose our perspective from ice core records in the most recent period because it's hard to get back out to ice core sites to update them and connect them to the present day. So our perspective on the last 2 decades of Antarctic climate from ice cores also becomes limited. We have best perspective over the last 200 years, but not the last 20 years. So I guess essentially what I'm saying is that we need to be everywhere all at once, doing all of the things, which we know is hard in Antarctica, but we got to still try to do it. So we're all familiar with this place. I'm going to plop on here all of the permanent research stations, which are by and large biased towards the coast, except for in West Antarctica, which of course provides a lot of motivation for me. It's a big place. You can fit the entire west coast of the US there in that gap between research stations. We know that's partly because it's a nasty place, a lot of storms, bad sea ice conditions. But of course we have to be there because that's where we're seeing all the change in Antarctica, okay? Red is bad, it's the surface lowering as observed by ICESat-2 and ICESat. And by and large that change in the ice sheet is happening in West Antarctica. We all know that. So enter ice rises, my favorite feature in Antarctica and a favorite feature of ice core scientists, as these coastal domes that are appropriate for ice core drilling that ring the Antarctic continent and give us the opportunity to fill in this gap where we don't have long-term climate observations from research stations or any other means. We love these features as ice core scientists and glaciologists because they contain a lot of information. From a climate perspective and a past ice flow perspective, they have relatively simple layering that we need for interpreting stratigraphy with depth. They have limited crevasses for safety of operation. They're elevated above the ice shelves. They get warmer and melt in the summertime. They have thick ice, so you can potentially reconstruct back thousands of years if you can drill to bedrock. And then they have this unique structure underneath the divide called the Raymond arching, the stiffening of ice in that particular ice divide flow regime that brings your isochrones, upwarps them, makes them a bump slightly closer to the surface, which gives us a little bit of an advantage capturing more depth, more age with depth than we would otherwise get at a flank site. And I won't go into the various processes that are interacting along the changing West Antarctic coastline because I think we're all pretty familiar. Everything's interacting, ice, ocean, atmosphere, and the solid earth. And so we all want to bring our different toolkits and understanding to bear on that. And I think ice cores can really give us a good annually resolved time perspective on a lot of these processes, the ones I boxed up in red in particular. And so I think we can get a start on that by not drilling deep at coastal ice rises, but going out in this mode of as fast as we can, getting 100 to 200 years of perspective, which unfortunately in a snowy place does require about 150 meter deep coring, which is as deep as we can drill without getting into a heavier mode of logistics. So again, we're excited to get out there and add. So these blue dots are where we previously, as an international community, have drilled ice cores. Ice rises are nothing new, and we now have added shallow ice cores at another site on the coast of West Antarctica called Canisteo Peninsula. And again, it gets us out to that region of change that we want to better understand. And ice cores, I think, are going to allow us to understand a bit more from an atmospheric and oceanic perspective right out there on the coast. And when I mean right out there, this is what an ice rise looks like from a couple tens of kilometers away. This is Martin Peninsula, my favorite ice rise site where we were trying to get to on this most recent cruise, but had to divert due to regional sea ice conditions and safety considerations. But again, we're interacting. Everything is happening here right at the atmosphere-ocean ice interface, and having an ice core on top of that dome is going to be really strategic. So the previous slide was looking there where that arrow is pointing on the left. This is the Sentinel satellite animation of what's going on in the region that we're all pretty familiar with. Canisteo Peninsula is there on the right where we diverted to and collected our cores. So this is the journey we went on, a 55-day cruise with 13 days off the ship for ice coring. at Canisteo Peninsula there, the blue dot. This is what it looks like in closer view. We were able to get right up to the edge of it and start helicopter operations to establish our camp about 20 kilometers from the ship. Brought a lot of equipment in, a lot of flights, and then set up so we could do the ice core drilling, a site on either side of the divide, 500 meters off the divide on either side. And then the lines here across the ice divide show the radar surveys that Vikram Goel from India conducted over the 2 weeks that we were there. So this is a bit of what it looks like, just hopping off the ship as quick as you can, getting over the open water to avoid that hazard, and then climbing up the crevassed edges of the ice rise, which preclude any other way of getting up on top of them from the ocean side. You work your way up over the edge of the ice rise, and then at the summit on the ice divide, we established our camp and went right into a 2-day storm, which we were willing to weather so that we could keep more quickly get back to work and get science underway. So after that, we were able to quickly get the radar system set up. Vikram did an extensive sort of 200 kilometer plus grid of high resolution radar looking at surface mass balance variability across the ice rise, as well as deeper penetrating radar, which give us a first look at the structure underneath the ice divide at this site. And we see it's sort of really mature Raymond arch there with even M-shaped double arch, which implies quite a few thousands of years of stability at the site, which is really great to see, and will give us a lot of information about the past flow history of the site. While Vikram was doing that, we were, of course, drilling, and as fast as we can, bringing up cores with the U.S. Ice Drilling Program 40400 drill, which worked really well for us. Quickly, the timeline, from putting in and losing a day and a half or so to a storm, we were able to set up the drills in 1 day and get underway, rapidly making progress down to our 150-meter depth target, which we stopped at, and then helped our Korean colleagues finish up their drilling the next day before rapidly packing up. So in 13 days on site, we drilled for 7 days and collected 2 identical 150-meter cores on either side of the divide. And super grateful for my U.S. teammates, Julia Andreasen, who you heard from a little bit ago, and Etienne Gross. So it was time to pack it up. So we boxed up and slung all of our cores back to the ship, where a fire line of folks helped get them rapidly from the heli deck into the 2 freezers on the ship, with 1 core in either freezer for redundancy in parts of either core if any freezers went down. These operations worked really well. Communication was good, and everything came off safely. We were really pleased with all of it. So we demonstrated with the teams that we can do pretty significant ice coring supported by helicopter from RV Iran. And we got these 2 partner cores to both sort of help the Koreans get their analyses developed for ice cores and reconstruct the last 100 to 200 years of climate forcing right in the Amundsen Sea. So really gratifying to finally get this fieldwork done. We hope that we can add that to future cores along the coast, things like what Julia was alluding to, and also not forget about the Inland West Antarctic Ice Core Array, which is now about 20 years old and is in need of updating with really shallow hand auger coring. Hope we can get to that sometime in the next 5 to 10 years. While we were finishing up our science time in the Amundsen Sea, the University of Texas and Montana State folks got excited about some of these ice rides after seeing what we could do, and they were gracious enough to spend a day and a half of their flight time flying over Martin Peninsula, which is a future target for us, to get some additional radar imagery that complements the existing NASA Operation Icebridge flights over that site, which is a great one for shallow ice coring and even potentially deep ice coring with access overland from interior West Antarctica. So I'll stop there for time, and I'll just remind folks, particularly early career folks, but myself as well, what's all of our dream project for 10 years from now, right? You need to have the things you're working on now, the project you might be doing for your PhD supervisor or your postdoctoral supervisor, but also think of the big pie in the sky stuff that you want to do in the future, because it's so, that's the order that it takes for some of these more ambitious initiatives, particularly in Antarctica. So I'll just wrap up by thanking my partner in crime, Young-Chul Han, who was the most gracious collaborator I could ever imagine, as well as Wansang Lee, who was the chief scientist on the Thwaites cruise, and Seok-Young Yun, who led the marine operations. So thanks very much. Hope you guys have a great last day of the workshop.
All right. Thank you, Peter. There's time for a quick question for Peter. Right. All right, so next we're going to hear from Gemma O'Connor.
Okay, hi everyone, I'm Gemma. I'm a postdoc at the University of Washington, and I'm happy to follow Peter and Julia's nice talks about the climate in the Amundsen Sea and kind of connect that to the ice shelves by looking at the ocean. So I'm going to talk about how polynyas and meridional winds can provide an atmospheric explanation for the drivers of Western Arctic glacier retreat. And this is work that I've done in collaboration with several people, and I particularly want to thank Yoshi Nakayama, who played a huge role in this work. So we all know Western Arctic glaciers are rapidly melting, in particular via exposure to warm circumpolar deep water, or CDW. This figure on the left from Adusumili and co-authors nicely shows why that's happening in Western Antarctica. It's the part of Antarctica that is exposed to really warm ocean temperatures along the coast. And if we look at a side profile of what the ocean looks like in the Amundsen Sea region, we can see that there's cool winter water on the top, warm, salty circumpolar deep water on the bottom, and the way that that circumpolar deep water makes its way towards the ice shelves is from this eastward undercurrent of circumpolar deep water, which lies at the shelf break. So when that undercurrent gets stronger, that transports more circumpolar deep water towards the ice shelves through these troughs in the bathymetry. So the glaciers have been retreating ever since we've been observing them. There's evidence from sediment cores that this retreat started sometime in the mid-20th century. And in order for that to have happened, there must have been some sort of change in the ocean to have caused that. And it would make sense for that to be an increase in the amount of circumpolar deep water that has made it towards the ice shelves. And for an increase in CDW to have happened, there must have been an atmospheric forcing to trigger that change in ocean circulation. But since we have limited observations, we don't know what that atmospheric forcing could have been. So strengthening circumpolar westerlies are a common culprit in trying to explain why this is happening or why this did happen. And that's because of this relationship that Julia has touched on before, which is that shelf break westerly anomalies tend to be associated with a stronger undercurrent and therefore more CDW transport and more ice shelf melting. And this has been a finding from a few studies which created this pretty seminal relationship connecting shelf break westerlies to enhanced CDW transport. And Knut and co-authors in 2022 kind of extended this relationship and showed that it does hold throughout the 20th century. So they forced a regional ocean model with historical climate model simulations from the Pacific Pacemaker Ensemble. And that ensemble shows westerly trends over the shelf break region. And what they found is that when they forced their model with this westerly trend, they did find simulated ocean warming on the shelf, and that was associated with enhanced ice shelf melting. So they kind of put all the pieces together to this puzzle. The westerly trend leads to enhanced ice shelf melting. So that was very nice to see. The problem with that is that this all rests on the assumption from climate models that this westerly trend actually happened in historical record. And climate model simulations have very few data constraints, but we can look at proxy reconstructions that were published in the last few years, and surprisingly, those proxy reconstructions actually disagree with the historical climate model simulations. They show no evidence of a westerly trend, and that's because they show this robust Amundsen sea low deepening pattern, which places northerly winds over the shelf break region, as you can see here. So yeah, I published some of these reconstructions, which didn't make me very popular in the community because I poked a hole in this narrative, but other people have also found this as well. And the reason that proxy reconstructions and the simulations disagree is simply due to how noisy the climate is. So now the question is, can on-shelf northerly wind anomalies be the historical driver of enhanced poleward circumpolar deep water transport in this region? So I decided to look into this by taking a sensitivity approach with some numerical ocean modeling experiments. So I'm using a regional domain of MIT GCM. This is the domain that I'm using. And I'm following the configuration from Yoshi Nakayama and others from 2018. And I conducted 10 simulations, which were all forced by different atmospheric forcing. So I wanted to see if you just threw a bunch of different wind patterns at the model, how does the ocean circulation respond to that? So these are the 10 different wind patterns that I chose as forcing. I just randomly drew them from the ERA interim observational record. And so I drew them year by year. So I drew 1 year from ERA interim, and then I repeated that year 5 times, so that each one of these wind forcings that you see was used to force the model for 5 years. So for example, this member, which shows a really strong westerly forcing, the simulation would have shown 5 years of strong westerly, so you can see what the response is to the cumulative effect. So yeah, I ran the simulations for 5 years. It has dynamic sea ice and a thermodynamic ice shelf, which means that a caveat of this, which is the same as caveats from previous studies, is that the focus here is on local atmospheric changes, and also you can't evolve the ice shelf geometry. So moving on to the results, I'm focusing on surface changes here, and this column is showing the ensemble mean, so just what the natural state in the model looks like. So we've got winds, sea ice area, and surface heat flux. And then this is showing anomalies in the warm composite. So I took the 4 simulations from the 10 that I conducted, the ones that led to the most ice shelf melting, and I composited those to see what the surface patterns looked like. And those did lead to a 40% increase in ice shelf melt after 5 years. So what you can see is that the anomalies in the warm composite are northerly winds relative to the ensemble mean. And those are associated with decreased sea ice extent, which means that these coastal polynyas are closing up in the warm composite. And then consistent with those closed polynyas is positive surface heat fluxes, because sea ice creates this insulating effect, so there's less surface heat being lost to the atmosphere. And what you see in the cool composite is the opposite response. So we have southerly winds, which is blowing the sea ice away from the coast, opening up the polynyas, and you're getting a ton of surface heat loss near the coast. So how do these northerly winds and closed polynyas actually lead to this 40% increase in ice shelf melt? So next I'll focus on the warm composite anomalies to explain that mechanism. So here we're looking at temperature, salinity, and zonal velocities in the warm composite, and the rows are showing each year in the simulations. And just as a reminder, I'm using the same forcing for each of the 5 years in my simulations, so they all are a response to northerly wind anomalies and closed coastal polynyas. So what we can see is that after a couple of years of these polynyas being closed, there's a huge insulating effect. So we get a ton of warming on the inner shelf, and that enhances ice shelf melting. So that floods the inner shelf with freshening, which is also a response to the decrease in sea ice production. And that freshening creates this cross-shelf density gradient, which causes this shelf break undercurrent to become stronger. And that's due to this kind of confusing thermal wind balance. But previous studies have also found this mechanism. And then once that undercurrent of circumpolar deep water strengthens, that supplies more circumpolar deep water towards the ice shelves, so you get more warming on the inner shelf and more ice shelf melting, which means that this continues to get stronger. So the density gradient gets stronger, undercurrent continues to strengthen. So those are the results of my simulations, which kind of connect northerly winds, closed polynyas to enhanced ice shelf melting. I wanted to see whether this persisted over the full 20th century. So I looked back to Caitlin Naughton's 2022 ensemble, where she forced an ocean model similar to the one I used with the historical pacemaker ensemble, which showed the westerly trends. And she focused on the ensemble mean from those simulations. And here I'm doing a composite analysis to see what is leading to the warmest conditions in her simulations versus the coolest conditions. So on the left is the warm composite from her simulations, and these are showing trends over the 20th century. So you can see that there is a westerly trend in both the warm composite and the cool composite, even though the cool composite doesn't lead to warm conditions on the shelf, and that the difference between the warm composite and the cool composite is actually northerly winds. So that was really nice to see that it nicely agrees with the results from my simulations. So just to conclude, we have more pieces to this puzzle now. So we know what the historical forcing is from proxy reconstructions, which shows a northerly trend over the Amundsen Sea embayment. We now have, from these new simulations, a mechanism that connects the northerly wind trend to enhanced ice shelf melting, and that's due to changes in the coastal polynyas, which causes changes in the undercurrent at the shelf break. And then we have further support for this mechanism persisting over the full 20th century because of the simulations from Naughton et al. 2022. So yeah, that's really nice to put all the pieces to this puzzle together. A key finding from this is that shelf break westerlies are a poor indicator of ice shelf melting, so it kind of cautions against using that, and also emphasizes the importance of local sea ice changes and surface heat fluxes. And I know I'm out of time, but one last thing I want to plug, this really cool web app that my undergrad student Jordan Tucker made. So if I've piqued your interest at all in using proxy reconstructions, and you're interested in using them, if you feel limited by using ERA 5, which stops in 1979, and you want a longer climate record, you can go to this web app and play around with the proxy reconstructions, because yeah, there are a ton of them, and it's not clear which ones to use, so it's just nice to be able to see how they do in different regions. So yeah, thank you.
Thank you, Gemma. I think we'll move on in the sake of time, so hold your questions for the discussion. And next, we have another student. Okay, I made sure I could pronounce his name. It's Rohaiz. Take it away.
Go to test the laser pointer. Old school. All right. Hi, I am Rohaiz. I'm a first-year PhD student at Colorado School of Mines, and today I'll be talking about some of the work that I did last year as a summer undergraduate research fellow at Caltech with Mugen Gupta, Skylar Grain, and Andy Thompson, where we investigated surface momentum transfer in sea ice covered regions and how flow scale dynamics might play a role in this. So just to set the scene, we're looking at a map of ocean velocities that was taken from a simulation of the ocean, and we can see that there are these thin jet of fast flowing ocean currents all around the Antarctic coastline. And these regions experience high shear, and they help to mediate transport between the open ocean and Antarctic ice shelves. And it's important to be able to constrain the momentum budget of these regions. For example, we've been hearing a lot about heat flux towards these ice shelves, which is what a lot of us in the WAIS community are interested about. So typically, these regions tend to be covered by sea ice, which also help to mediate momentum transfer between the ocean and the atmosphere. And we usually model sea ice as a continuum in global climate models. Sea ice tends to be broken up into discrete flows. We think it's important to be able to represent the discrete nature of sea ice in order to capture these flow-flow interactions. And so we try to see if flow scale features influence momentum transfer in the pack using a more realistic representation of sea ice. We do this by using Sub-Zero, which is a novel discrete element model that was developed by our collaborators, where flows are modeled as polygons, which is a more realistic flow geometry. The flows can carry translational and rotational motion. They're advected around due to forcing from the ocean. They can also collide with each other and transfer momentum that way. So in our experimental setup, we impose an idealized shear flow in the ocean, as you can see from the orange arrows and the curve, and it peaks at 0.5 meters per second at the center of the jet, and it goes to 0 towards the edges of the domain. We run two sets of experiments, one where we vary only the pack concentration and we keep flow size the same, and another where we vary flow size and we keep pack concentration the same. So here we're looking at a snapshot from one of these experiments of 90% concentration, and the color map that we're looking at represent the ice ocean stresses. So we can see that at the center of the jet, we get these negative ice ocean stresses that come about when your ocean moves faster than the sea ice, and so it's dragging on the sea ice. But then you can see that as you go towards the edges of the domain, you start to get these positive ice ocean stresses, which come about when your sea ice is moving faster in the ocean. So we can already see that sea ice is capable of sustaining this momentum and transferring it meridianally across the pack. Now, if you look at an experiment of lower concentration, 80%, we see that the ice ocean stresses are a lot smaller. So visually, we can already start to see that there is some dependency of this momentum transfer on pack concentration. we want to start thinking about how the pack deforms in response to the ocean forcing. And so we take the zonal and ensemble average velocity profiles of the sea ice flows that's calculated from grid interpolated ice velocities, taken when the model reaches steady state. And we sort of see the same story here. So if you look at the 80% experiment, which is this green dotted line, we see that the sea ice once again moves slower than the ocean at the center of the jet, and then it starts to move faster as you go towards the edges of the domain. And so we can see that these variations in the sea ice velocities is kind of an indicator of the pack deforming in response to this ocean forcing. But now if you look at experiment of higher concentration, so the red dotted line, 90% concentration, you see less variations in sea ice velocity. And so we can see that a highly concentrated pack is able to resist this imposed deformation. We see a similar story when it comes to flow size, where a more rigid pack resulting from larger flows is also able to resist this deformation better. So we've already started thinking about deformation of the ice pack, and we can quantify this by the shear strain rate, which is the derivative of the ice velocity profiles we just looked at. With respect to the meridional direction, we also want to start thinking about the shear stress that the pack is experiencing. And we know that at steady state, and when you take the zonal average, the derivative of the shear stress with respect to the meridional direction is actually equal to the ice ocean stresses that we just saw in those colorful plots earlier. So we integrate that to get shear stress. And going forward, we want to see if there's a relationship between shear stress and shear strain rate. And if so, is there a dependency on pack concentration or flow size? So we plot the shear stress against the shear strain rates for one such experiment. And we see that there's this range of strain rates where there is a linear relationship between shear stress and strain rate. But then beyond this range of strain rates, we see this plastic behavior where the pack starts to experience maximum shear stresses. And now when we plot experiments of varying concentrations, we can see that within this linear regime, the slope of the strain rate curve is actually increasing, which is indicative of a highly concentrated pack being more efficient at transferring momentum meridionally across the pack. And we can also see that a highly concentrated pack can sustain higher shear stresses. We see a similar dependency on flow size, where as you increase the flow size of the pack, your pack of larger flows is more efficient at transferring momentum meridionally, and it's also able to sustain more shear. So we believe that this dependency on pack concentration comes about from the following mechanism, where when you get a higher pack concentration, you get more flow-flow interactions through collisions, which lead to more momentum transfer. And something that we're currently working on is figuring out what is the mechanism that gives rise to the dependency on flow size. Another thing to note is that in all of these experiments we've looked at, we're imposing an ocean forcing that does not evolve in time in response to these interactions with sea ice, which is clearly not the case in real life. So we are currently working on coupling our CS model to oceananigans, a non-hydrostatic ocean model. And we're imposing a shear forcing through the atmospheric winds. And we can see in the left panel, which represent the ocean U velocities, that you can see a shear being developed in the ocean as well. And we can also start to see that these flows are experiencing a rotational component. So we are seeing a more complex momentum budget when considering a coupled sea ice ocean model. And something that we're also trying to do is implement more realistic forcings, where we're looking at taking wind speeds from Era 5 data for regions around Antarctica that might experience these boundary currents, such as the Ross Sea, and forcing our model with that. So some new stuff to do. So just to wrap things up, we used the discrete element model to explore how flow scale properties of sea ice can influence momentum transfer. We found that a more rigid pack resulting from larger flows or a higher concentration can resist deformation better. It transfers more momentum meridionally, and it has potential to weaken the ocean jet more efficiently. Continuum models don't capture this flow scale dependency and may misrepresent this momentum transfer. And I'll just sort of leave you with that and take any questions. Thanks.
We do have time for a quick 1 or 2 questions for Rohaiz.
Okay, yeah. Well, that was a great talk.
Thanks.
I was just curious, from that picture of the ice flows, it looked like there was like a very large distribution in sizes for the for the real ice flows. So I was just wondering if you can comment on like the distribution of sizes in your simulations and if it reflects the reality and like if you've looked into
Of course.
changing those distributions.
So currently we are in these models, we're not considering the flow size distribution within the pack, but you're extremely right. And I think that's one of the new kind of features that we're working on, implementing a more realistic flow size distribution within our pack. And since you kind of brought it up as well, I'll also mention that our flow thickness distribution right now is just uniform, which is also not the case. We can impose varying thicknesses, which is something that we've been doing. But you kind of get this like normal distribution, which is also not what you see in real life. So that's another one of the features that we're working on for Sub-Zero, implementing a more realistic flow thickness distribution. So hopefully, you know, the goal is to get to something a lot more realistic.
Cool.
All right, thank you, Rohaiz. We can move on. Next, we have our, I believe, final speaker. Zachary Katz, sorry, who is also a student, so please get your evaluations in.
Hi everyone, my name is Zachary. As mentioned, I am a PhD student at Colorado School of Mines, and we've been thinking a lot this week about one of the challenges in maybe connecting small-scale processes to thinking about how they can interact with larger processes, for example, in models. And I want to show today how we can use observations to help scale that gap. And in particular, I'm going to be working on some work I worked with Matt and Lori about how ocean tides, one of these shorter scale processes, modulate ice flow on a longer time scale on Willen's ice plain. Zooming out, we have this great record of long-term ice sheet motion. I'm just showing the 20-year average in this plot, but we also have yearly records of what the ice sheet is doing, and we know that it's a really dynamic system, changing year after year. But there's a fundamental limitation in this large-scale record, which is the satellite orbit repeat times. We only have this yearly product, and satellites orbit weeks to months, so you only get records on that time scale. And in order to get a finer temporal resolution, our current limitation is that we need to zoom in. So that's what I did, is I zoomed into the Ross ice shelf, and particularly Willen's ice plain, to look at how one shorter-term process, the tides, is leading to the long-term variability that we see. This cartoon is showing that the tides impact the ice shelf in a variety of ways. One is the tide grounding zone, as we now know to call it, moves back and forth. The ice shelf flexes up and down with the tides. And perhaps most importantly for this talk, that the long flow velocity is also dependent on those tidal processes. And one way that we can get at what the tides are doing to the ice shelf is to use GPS data. So if we place a GPS station in the ice sheet, and then we let the ice sheet flow, we can record its position. The GPS stations that I'm using have a temporal resolution of about 15 seconds and are able to get a really high temporal resolution, but the spatial resolution goes down to a single point. This is partly mitigated by the study site that I'm using. So if you think of that cartoon, and now we're looking at it in map view, I'm looking at Willen's ice plain in the southern Ross ice shelf. We have the ice flowing from the left, crossing the grounding line, which is moving back and forth with the tides, and going onto the ice shelf, which is flexing up and down with the tides. And each of those white triangles is a different GPS station that's been part of one of the field campaigns that's been going on in Willen's from over 11 years, 2009, 2007 to 2019. So each of these is stations, so we have this wealth of data and are able to better understand the processes of what's going on. Now I want to show you a time series of what some of this GPS data looks like, and this dates back So there's about 5 days of data here, and each of those individual gray lines is a record from a single GPS station from these more modern records. But this has been going on at this conference and on this ice stream since the 1990s, this idea that it's stick slip motion. The GPS stations, which I've just all moved to start at 0, and I'm just showing the one component, the X displacement here, all move about 12, 24 hours fairly steadily, and then we have a slip event where they all move about half a meter fairly together, and it moves steady, and then so we have a stick, and then a slip, and then a stick, and then a slip. And you can see that those slip events are highly nonlinear, and that suggests a way that I'm able to, now that we have this wealth of data, to understand how they are, to automatically detect them. And so I can take a linearly squared SFIT, which is this amber line, and then detect the residual. And there's spikes at each of the events in the residual where it goes nonlinear and you have this event. And then you can threshold it and then take anything above a threshold and consider that your event. I mentioned that it's these 12-hour periods or 24-hour periods between events, and that's because they're correlated to the tides. But now that we have this long-term record, we can think more holistically about how the tides are also changing in the region. So this is just showing a time series over 6 months of what the modeled tides look like in front of Willand's ice plain, and we can see some characteristics. The main tide type is diurnal, one high tide every 12 hours, and the triangles are just showing the tidal extrema. But we also have semi-diurnal tendencies, so that's a high tide every 6 hours that go inside the outer tidal envelope. And then those two constituents beat to produce fortnightly tides. That would be your spring and your neap tide, those large lobes that you see on the plot. And so we can take the events and plot them on this plot. So each of the dots is now an event. I've colored them since the last event, and then I've also plotted them at the tide height of the event. And as previously noted, these events follow the tides. They're along the upper part of the diurnal tides, but when you have these semi-diurnal tides, they move away from the outer envelope and agree with when the semi-diurnal tides are occurring. This is just 6 months. I told you I had 11 years of data, so we can zoom out and see what that looks like. So here's all 11 years. The gray bars are showing when we didn't have GPS data, but you can see a trend that has been seen in previous portions of this data is that there's a decrease in the number of low tide slip events. In 2008 to 2010, there's lots of dots in the negative 100, negative 150 centimeter region, but as we move towards 2018, there's a lot less dots. And I don't know about you, but it's sometimes hard to look at 5,000 dots and make a little bit of sense of it. So we can take some averages over this long term since we have this long-term record. So that's what I'm trying to do here, is that I'm taking a 45-day window and then just dividing by the 45 days to get an average number of slip events in that, per day in that window. And we see we get the same exact trend. We go from 1.8 events per day, that would be a primary slip event and a secondary slip event in the record, going down in 2019 to 1.2 slip events a day. That would be just one slip event over the record. But perhaps more interesting is a sinusoidal trend. I've marked in the brackets SSA, which stands for solar semi-annual, and that's a beating of the tides at about 185-day period that you can see in the tidal record, the gray bars in the back, and you also see in the record. So even though individual slip events may be seemingly random or randomly distributed with the tides, overall this is having some effect on the stress buildup in the region, and we're able to see how the tides are impacting the region. Perhaps this is more intuitive to look at if you look at a spectrogram. So this is just a spectrogram of that black line from the last plot. We have a large peak at that 185-day period. If you zoom in, you can also see a trend that aligns with the monthly tides also, this 25.77-day monthly period. But what's perhaps more interesting is that if you look at the tidal spectrum, so this is now a GPS station that's on the floating ice going up and down the tides, that spectrum only has the semi-diurnal and diurnal components. There's a whole lot of white space in that graph where the monthly tides, where those two peaks are on the other graph. And if you believe me, if you extend it out, there's a lot of white space where the solar semi-annual tides are also. So it's really the beating of the tides and this nonlinear interaction that's causing these long period tides to emerge and come out in the record. So this has some implications for studying ice streams. One is that the long-term high-resolution data set is essential to understanding what's going on at Willans. We needed that 15-second resolution to detect these half-hour-long slip events and build this record. And then we're able to use this long-term record in order to understand how that's affecting the tides on semi-annual, annual timescales. And another thing is that the variation in tidal forcings is important to consider when we're doing studies in this region. We saw that the number of slip events is varying greatly over periods as long as the semi-annual 185-day tidal cycle, and that needs to also be considered that the external forcing of the tides is changing what's going on in the ice stream in addition to any underlying glaciological changes. And finally, we need to think about when we model this that we typically use one or two components of the tide to force it, but we need to think that the solar semi-annual cycle and the monthly cycle that we see are both a result of the interactions of the beating of all these rich variety of tidal constituents that we use that we don't get when we just use one or two parts of the model, one or two constituents when we're making a model of this. Thank you.
All right, thank you everybody for the great talks. I'll invite all of our speakers up to the front to be questioned as a panel.
Also, we're going to abbreviate this slightly, so we'll do 15 minutes of this panel discussion and then move into a discussion of the kind of the broader goals that have come together from this meeting, talking about future science for WAIS. But we'll start with questions for this specific panel. So, Bree.
It's a question / comment. You know, at the Willans Ice Stream Grounding Zone in the Wizard Project, there was one instrument that was run, and maybe you know about it, maybe you don't, and maybe it would be useful, and maybe it wouldn't, but Ross Powell's IPSI package, which had a downward-looking camera that we were recording, and in real time, you could see the bottom, and we captured a slip event in real time on video, and that's a very different perspective on it, and I don't know whether just having seen what actually happens, maybe the lead in and lead out might be useful to you if you didn't know about it.
Yeah, no, I hadn't heard of that, so that would be extremely useful. There's a whole lot of basal processes thinking about how the basal conditions are changing as the tides flow in and out of that also are causing this stickiness and the stick slip motion. That would be really helpful to see a video like that to see what exactly what's going on.
This was at the grounding zone. You know, you could see some rocks, and all of a sudden it starts moving, and it moved for a little while. And I'm not sure if that data was properly archived and accessible. I can ask Ross, but otherwise we definitely have copies of it, so you can get in touch with me if you can't find it.
Yeah, I had another question for you, Zachary. So you framed everything. First of all, really great presentations, all of you, and I really liked how you visualized the long-term time series. You framed everything in terms of the number of slip events that happened. I'm curious, did you also have a chance to look at how large those slip events were, in distance traveled, and is there any trend happening there?
Yeah, that's a great question. There definitely is a trend in terms of what's going on with the actual individual events. I focused on just some sort of long-term statistics and the actual event identification for this presentation, but I've also been looking into the fact that even though there's stopping of slip events, the other ones don't, how we started with 2 events per cycle going down to 1 event per cycle, that 1 event is not twice as long as the other one. So there's some sort of stress buildup, for example, in the viscoelastic regime that is happening there. And then another thing that's really interesting to look at is the inter-event motion, because that is also sort of changing on timescales.
Thanks.
Zachary, can you expand on that? How is the inter-event motion changing?
Yeah, no, I don't have a definite answer, but we've been looking into that on this long time scale, there is some change that we're seeing.
Hi, Michael. I really wanted to get to stand up and just say how much I enjoyed that and appreciate what you have been doing. In a way, when I look at your Bouguer anomaly interpolations, I look to the geologists in the room, because it's a little bit like everywhere that you have a constraint is a rock exposure, and you're building all these possible maps of how to put them together, and I'm excited about that. I wanted to ask you a question. Since you're trying different interpolations of the Bouguer anomaly between the constraints, have you also got built into your process different interpolations of the measured free air anomaly across the gaps between flight lines? Because some of the places that we're working have like really distant flight lines, and there's different ways to draw those lines. Can your process do that as well?
Yeah, that's a good question, and first of all, thank you. Yeah, one thing I should mention is that we upward continue the free air anomaly onto a plane so that we can actually do 2D interpolation. So that upward continuation in itself provides some interpolation, and then we mask that so that it doesn't go too far away from where the original measurement locations were. And I have thought about ways to introduce uncertainty into that upward continuation. But no, at this time, I'm not sure how to actually do that. So yeah, that is another interesting component.
Yeah, thanks again for constraining all the uncertainties of the process that we do, and between the geologists and a lot of the other people in the room who need to know exactly where this basin or this peak is, I think there's a lot in your tool that we can use.
Thanks for giving me the data to do that.
That was a really great set of talks. Thank you, everyone. Michael, I have a question for you as well. I really enjoyed your talk and was especially excited to see all the various types of aleatoric and epistemic uncertainties represented there. I was curious, when you were looking at the uncertainty maps that came out of not the mean, but the standard deviation of your maps, there seemed to be some spatial correlations of areas of high uncertainty. Do you have any thoughts about what unknowns, I know they are unknown, but maybe what unknowns might be contributing there?
Yeah, certainly. And if you remember the uncertainty of the SGS, you might have noticed that the uncertainty in the SGS ensemble, the standard deviation, does kind of follow that same shape because the SGS is really driving the uncertainty there. In terms of the sources of the uncertainty, interpolating the Bouguer disturbance is kind of an indirect way to get at some of the subsurface geology. So if we break down what we're actually saying with those interpolations, we're saying something about sediment thickness potentially, or intrusive igneous rocks in kind of a roundabout way. So yeah, that's kind of the best physical explanation I can give right now.
You can go. Rohaiz, I have a question for you. I'm wondering if your modeling can be used to go from like pre-breakup sea ice to try to model like the actual breakup process.
That's an amazing question. I'm really happy you asked that, because one of the new features of Sub-Zero that I did not mention in my talk that makes it different from other discrete element models is that the flows can actually fracture. So we're running all of these simulations without the fracture process, but you can impose a fracture criteria, and the flows will fracture, they'll change shapes, and that's something that's really exciting. And we did briefly explore adding this fracture process, but the fracturing is only going to be as good as the criteria that we're imposing. So I think going forward, we'd want to be sure of what yield criteria that we want to impose before adding that feature in our simulations. Thanks.
Gemma. I'm still framing this in my head. So we've been doing this like Spider-Man GIF thing for a long time where the glaciologists are like, it's the ocean, and then people like you are like, no, it's really the atmosphere, and then Eric Stagg 10 years ago and Julia today, no, it's the teleconnections. And so we go in this roundabout circle, but I really loved your comment that the local scale features are the thing that modulates a lot of how the forcing is felt. And so I think back to the paleo record at that point where it's like, how have you thought about how what you are doing on the kind of forcing side makes us reinterpret paleo records, right? Like maybe it's just polynya dynamics modulating a forcing somewhere and processes like that.
Oh, interesting question. Yeah, I haven't thought about sort of the coupled dynamics between like the effect of sea ice on the atmosphere. So, I mean, the results from my findings have just kind of opened my eyes to sea ice, and I think that's an interesting direction I could go in. So yeah, I'm thinking about working with Ed Blanchard Wigglesworth on that since he's a sea ice person. So if anyone knows how sea ice can affect the atmosphere, I'm interested in learning more about that. But yeah, I couldn't tell you right now.
I guess my question sort of follows on nicely from Matt's, but I was thinking about the Ross Sea, and I think there's some evidence that the same mechanism that you proposed is happening, where like the density-driven change is driving more circumpolar deep water onto the shelf. I just wondered if you had any ideas or perspective on how that might change in areas like the Ross Sea where you have bottom water formation happening. Like, is that sort of, and again, like linking into the paleo record, like is that sort of mitigating like that warmth coming onto the shelf because it's blocking it a bit more, like with the cold? Yeah, I just wondered if you had any ideas about that.
Yeah, I'm super interested in learning more about how this mechanism acts in different regions of Antarctica, and I admittedly only focus on the Amundsen Sea, so I'm interested in learning about these relationships with places like the Ross Sea. So yeah, I should look more into how that changes things, because I think the Ross Sea has a huge polynya also that, yeah, is causing these dynamics. But what was your question about how to make these connections?
I guess, yeah, I didn't really phrase it super well, but I guess my question is like, is this mechanism important in the Ross Sea today? I think we don't know that, right? And so, yeah, I think just understanding the modern processes will help inform the paleo record a bit more, like the exact mechanism that's driving ice retreat.
Oh, yeah. Yeah, I guess I agree with your question. I can't provide an answer.
That's okay. Yeah, we can talk more.
That's really
perhaps.
interesting.
Yeah.
Yeah, thanks for that.
I also have a question for you, Gemma. It's similar to Matt's and Imogen's questions, which is, have the modelers really that predicted the westerly winds causing the changes in ocean circulation started to take into account your findings, and how do those like synergies work?
Yeah, it's interesting because I'm going around saying lots of people are interpreting their results incorrectly. But yeah, I do work closely with these groups, so I'm not just talking behind their backs. Yeah, so like Paul Holland and Caitlin Naughton from the British Antarctic Survey are people who published some of those studies. And also my PhD advisor, Eric Stagg, is also one of them. So he was highly motivated to prove me wrong and was unable to do so. So I think we are having these discussions, and it's interesting to think about why these apparent discrepancies exist. And I think there are several reasons to explain it. Like I think Eric's 2012 paper, and there's a Toma et al. 2008 paper, which sort of started this finding that connects the shelf break westerlies to enhanced circumpolar deep water transport. And those are based on really coarse resolution ocean models. So I think one explanation is simply that they were just too coarse, that they couldn't distinguish conditions from the shelf break from conditions on the inner shelf. And that does agree with what I found, because I'm finding those changes are highly local to the shelf break, but they don't extend to the inner shelf. Another reason is it could just be a timescale dependence, because their focus was on seasonal changes, and it could be that it doesn't hold on longer timescales. And then another explanation compared to the British Genetic Survey's results by Paul Holland and Caitlin Naughton is that they focused on ensemble means, and I think it's important to focus on individual members because the climate is just so uncertain, and I think that's why proxy reconstructions are so valuable, because they can kind of say which within that ensemble spread was most indicative of historical conditions, whereas the ensemble mean is just showing you what the most likely outcome is. So yeah, it's really important to have these discussions.
Any last questions for this panel? Okay, if not, we will move on to a more, first. Thank you all.